Welcome, students, to online learning. This is definitely going to be a new experience for us. I do apologize if you end up hearing kids, dogs in the background. I'm trying to use headphones. That's why it might sound a little bit funny. This is my third time recording this video, so hopefully it'll work. There is a time limit on YouTube. I went over the time limit, all that fun stuff. So if your professor in another class is using some software you think might work better for this class, I would love any recommendations that you have. You'll see when I start typing stuff out, it's going to be a little bit messy. Since we only have a 15-minute time limit, there will be several videos posted per day per lesson because I can only make short videos. So let's jump right in. We finished last class talking about acid-base indicators. Once again, please make sure that you upload your experiment 5 acid-base titrations to Wolfden by Wednesday. That would be appreciated. We are done then with acid bases, and we are moving on to talking about other equilibria classes. So our next class of equilibria is solubility. Last semester, we talked about things being soluble or not. If it's soluble, that means it dissolves in water or in some solution. If it does not dissolve or it only dissolves partially, we would say that it is insoluble. All ionic compounds are going to dissolve in water. So even though last semester we said that they are insoluble, they do dissolve just a little tiny bit. And once we start doing the math, you'll see that these concentrations are extremely low that they dissolve in. So we can talk about it in terms of equilibrium, right? We have some salt. Our salt will dissolve. We can then calculate the equilibrium constant or the solubility product constant, the KSP. So the KSP and the solubilities can be determined. We can do the K expression the same way we've been doing Ks before. So our equilibrium constant for the dissociation of some solid salt into its ions is called the solubility product constant. So here we have MnXM, right? It is a dissociation, so that is some solid salt. It is dissolving into M ions and X ions. We can then write the solubility product constant. So once again, normally, right, it would be our products over our reactants. Well, in this case, our reactant is a solid, so we don't even need to worry about it. All we need to worry about are our products. So our KSP expression would be M raised to the n power, right, raised to its coefficient, times X raised to its coefficient, which is M. An example here is the dissociation of PbCl2. PbCl2 is solid, right? If we had looked at our chart from last semester, we would see that it says that it is insoluble. But we know that it is going to dissolve just a tiny bit. So we will get lead 2 plus and chloride. We're going to have 2 of them. So the equilibrium expression would be the KSP of lead, concentration of lead, times the concentration of the chloride ions raised to the second power. Thankfully, we do have a table of solubility product constants. You would be given this table for a test. I'm going to try to put together a document that has all of our tables together so it's easy for you to access for your exam. Once again, your exam is on next Friday, so please make sure that you are able to take it on Chem 101 sometime next Friday. So we were looking at, we're looking at lead 2 chloride. If we look at the top right, lead 2 chloride has a KSP of 1.17 times 10 to the negative fifth. So we can use that KSP value to determine the solubility of lead 2 chloride. So the solubility is the maximum amount of solute that will dissolve in a given amount of solution at a particular temperature. So we're always going to assume we're under one temperature. Our temperature is not changing. But we're going to try to dissolve some salt in a solution. We can figure out how much of that salt will dissolve. As we said, these are insoluble salts, so not much of it will dissolve, but some will always dissolve. We can calculate the molar solubility. So it is in terms of molarity, right? It's moles that have dissolved of our solute per liter of solution. This would be of a saturated solution because if you think about it, you're going to put in some amount of salt, right? Some of it will dissolve, some of it won't. So that would be a saturated solution. In general, I apologize. I am a little bit sick. Promise I don't have corona. We can have an equation here that says the molar solubility is equal to, here we have some N's, KSPs. Don't worry about using this expression, this equation. We will use it via algebra, so you do not need to actually use this equation. But as you can see, your molar solubility is directly correlated to your KSP value. So that they are related. Sometimes we cannot compare them to each other based on the stoichiometry, but thankfully our dissociation stoichiometry would end up being the same in all the ones I'm going to give you, and so we don't need to worry about not being able to calculate the solubility. So what this looks like is, here it says calculate the molar solubility of lead 2 chloride in water. Lead 2 chloride we know is going to break up into lead ions and chloride ions, right? 2 chloride ions. We can also look up the KSP of lead 2 chloride. So the top right, it tells us it's 1.17 times 10 to the negative fifth. So our first step is to write our equation, our reaction, what's happening. We write our reaction. We say that our lead 2 chloride is a solid, right? It is going to dissociate into lead 2 plus and 2 chloride minus. So we can write the KSP expression, right? We can write our products divided by our reactants. So our products are our lead and our chloride raised to the second power, divided by, technically, right, it should be our reactants, but our reactant is a solid. Solids don't go in our K expressions, so it just ends up being our concentrations of our products. Once we have this expression, we can do an ice chart. So initially, we know in general that we don't need to use the lead chloride, lead 2 chloride, because it's a solid. So we only need to focus on our products. Initially, we don't have any products. There is nothing there. So those are both 0. We're then going to increase the concentration of our products, right, as our salt dissolves. In this case, they use S instead of X just because we're talking about solubility. If you want to use X, that's no problem. This is just to kind of help us distinguish between the different K values, since we do have so many. So our lead is going to increase by S. Our chloride is going to increase by 2S because we have a 2 in front of our chlorine. So at equilibrium, our lead concentration is S and our chloride concentration is going to be 2S. We can then plug those back into our KSP expression. So our KSP, we said, was lead 2 plus times chloride minus raised to the second power. So let's plug in the S for the lead, and let's plug in the 2S for the chlorine. They then simplified that. So if you square the 2S, right, you get 4S squared, and then you multiply the whole thing by S, we get 4S to the third. So our KSP equals 4S to the third. Then you need to do some algebra. You need to rearrange your equation. So they rearranged it to get S is the cube root of the KSP divided by 4. You would then look up the KSP on the previous page, right? We said it was 1.17 times 10 to the negative fifth. Divide that by 4, take the cube root. You would get S is 1.43 times 10 to the negative 2 molar. As you can see, that is an extremely small concentration. So lead 2 chloride in water, only 1.43 times 10 to the negative second moles will dissolve in 1 liter of water. So that is a very low concentration, a very low amount that is going to dissolve. Stay tuned for the next video.